Right, so we've got a worked example here for the complex numbers problem, locus of the argument of a quotient of two expressions. These are a little bit difficult to get your brain around, I think. So hopefully this video will help. Let's have a look at this particular problem. Curve S is described by the equation Z minus 5 plus 2i in brackets divided by z minus 1 plus 6i, and that to be equal to a right angle. Show that S is a semicircle and find its center and radius. So let's just have a look at one or two of the ideas behind this. If we're looking at the argument of a complex number. Well, let we express, let's say Z1 here as in exponential form, then that's going to be written as the magnitude times e to the I theta 1, where theta 1 is this angle here, and obviously the R1 is this length. So that's what that would be, and the argument would be theta 1. So the argument would be this this angle here. Then similar there for Z2. So if we want the quotient of Z1 and Z2, we could actually write it as the quotient of the magnitudes, and then e to the I, well, the difference of those two angles. All right, so that's one of the sort of underlying ideas. Now, if we want the locus of a point of a complex number Z, such that the argument of Z minus some fixed number Z1, could be 5 plus 2i, couldn't it? Could be anything, equals, let's say, 35 degrees. I'm going to use degrees here, even though the question's in radians, because it's a bit more convenient. So what we're doing, this is a kind of linear transformation here. So we've transformed our complex plane, if you like, by shifting it up here. So when we're looking at the argument, we're measuring our initial line from this point here. So basically, it's all those points along that line, because the argument of those with respect to this kind of reference point here is going to be 35 degrees. So this line here is the locus. It's the set of points that satisfy that. Okay, we call this a half line actually, because it's all the points in one direction from this particular point. Sometimes we talk about array. Half line is quite a common expression. Okay, so that is sort of a couple of underlying ideas. Now let's have a look at something. Well, what we're interested really is when we've got this quotient involved. So what exactly does this mean, and what does it mean geometrically when we say that? Say that in this case we want the set of points such that the argument of Z minus Z1 down here, divided by Z minus Z2 and Z2 here, is equal to 40. All right, so it's a bit easy to look initially just with some specific numbers. So imagine, for instance, we're making this 40 up from 60 and 20. All right. So therefore what we're saying is that the argument of Z minus Z1 is going to be 60 degrees. So that's going to give us this line here. Now, all right, that's our initial line coming out from there. And then this line is all points that satisfy Z minus Z2 is equal to 20. Right. So what that's going to do is going to give us this 40 degrees here. All right. So that's the difference. I mean, intuitively, I think you could It might be obvious that that's 40. We can actually show this is 40 as well. But just simply with a bit of geometry, if this is 60, then this angle here is going to be 30. If this is 20, then this angle here is going to be 70. So therefore that leaves 40 for there. So two different ways of looking at it. But yeah, so that is 40. Now that's what the requirement is that we want the set of points that that satisfy this. Now it's not just 60 and 20 that's going to do that. I mean, 61 and 21, or you know, uh, 55 and 15, so all of those will satisfy that. So this is not just the one single point, it's a whole set of points where these two will vary, but this will stay as 40. So the difference, if you like, between those two, the arguments for those two things will be 40. Okay, so now if we think about our circle theorems, then if we imagine this is the chord of a circle, then the angle that it subtends on the circumference is going to be the same right throughout. And if we're looking for it to be 40 degrees, then it's going to move around this circle here. Well, it's going to, if it's 40 degrees, it's going to move around a major arc of the circle there, all the way around from there around to there. Okay. Um, if it was so that is if it's less than pi by 2. If it's more than pi by 2, um, then um, then we're actually looking at the minor arc. So I've drawn here, actually, once I draw it, it looks more like 130 degrees, so that's what I've put in there. So that's what we've got with this. Now, where this is constructed, yeah, we see the argument of that one looks about 110, doesn't it? And this one here, well, this is a negative. So it's going to be 110 minus 20, so that's 130. So that's going to be the minor arc of a circle. So that's what we've got there. Don't want to get into this too much, but just to kind of illustrate, there are other cases. And also, just to kind of round that off, what happened if we were to flip this ratio over? So we got z minus z2 divided by z minus z1 equals 40. Right, okay, well, again, so we got a similar situation, but here, in order to get this, what we're looking at is, okay, so this angle is bigger than this angle then. So this point, and therefore this angle here, is going to satisfy that. So we've got a kind of different circle, same chord, but a different circle. And the requirement might actually be to for a negative negative angle. So that's a kind of similar argument, but we'll not get into that too much in this video. But that just I'll sow that idea in your minds. But we're sort of principally concerned with this problem, obviously, aren't we? So anyway, I think it probably becomes clear from that now that if our requirement is this angle is a right angle, then of course, remembering again our circle theorems, the diameter of a circle subtends a right angle on the circumference. And so so if the requirement is a right angle, then our chord is going to be a diameter. Yeah. And that's what will give us that. So it's going to be this semicircle around there. Now, the center of that is going to be the midpoint of this point and that point, which is 3 plus 4i. And then the radius, we can just calculate, well, if we apply Pythagoras to these two endpoints of the diameter to find the diameter, square root of that lot, and then take half of it for the radius, then we're going to end up with 2 root 2. So that is the radius of the circle. Right, so that is that. The other one, part of this is find the maximum value of the magnitude of Z. Well, I think when we draw it like this, we can probably see that the maximum value is well, basically this blue line. The length of this blue line will represent the maximum value. So that's the point. That is the point which is got the greatest magnitude, sort of furthest away from 0, 0. And that is basically the other side of the center. So if we draw a line through the center to this point, that's what's going to give us the one with the maximum magnitude. And that's well, this distance up to the center is, well, this is 3 plus 4i, not very clear, but 3 plus 4i. So that's 3 along, 4 up. So the length is 5. And then this bit is a radius, which is 2 root 2. So therefore, this maximum value is going to be 5 plus 2 root 2. Okay, so quite an interesting problem, a little bit tricky, but I think if once you've kind of got that, then similar problems with this sort of ratio here of these two expressions, then probably should be a bit more straightforward. So I hope you found it useful and interesting, and thanks for watching.